Hello, everyone. Welcome back to our course on abstract algebra. Before we go on and talk about group homomorphisms and group isomorphisms, I want to motivate those concepts by talking about how to compare groups. What we're going to talk about is how do we know when two groups are the same group, essentially, and when they are different groups. And that is part of a much bigger goal of ours, which would be to classify all possible groups. Now, that is a ginormous goal. What do we even know by classify? Um, if you want, we can characterize all possible groups, and that is itself a very difficult problem to be able to characterize every single group that there is out there. There is so many infinite groups. There are so many even finite groups. There are just so many. But let's start with the goal of classifying finite groups. And in fact, what one could try to do is the following. So let n be an integer, be fixed. And we would like to characterize all groups G of order n. So we would like to know what are the possibilities for groups such that their order is n. And now we are really not equipped to do this because we don't know how to compare groups. But let me give you one early example of a comparison of two groups. So here is an example. I'm going to write two groups by their Cayley table. So one that we know is z modulo 4 z. Under addition, their Cayley table is 0, 1, 2, 3, 0, 1, 2, 3. And let me just write it down. This is 0, 1, 2, 3 because 0 is the identity, and 0, 1, 2, 3 because it is abelian. And then 1, 2, 3, 0, 2, 3, 0, 1, and 3, 0, 1, 2. Okay, so that is the Cayley table of this group z modulo 4 under addition. So now I'm going to give you another group, G star, where G itself is given by, it just has four elements. I'm going to call them A, B, C, and D. And I'm going to give you a Cayley table of this operation for A, B, C, and D, A, B, C, and D. And I'm just going to write it down. The operation works like this: C, D, B, A, D, C, A, B, B, A, D, C, and A, B, C, D. So this is a group. I can tell you that it is a group. And now the question is, is z modulo 4 the same as this group G? And a priori, it doesn't look it because, well, for example, okay, so here I have 0, 2, 0, 2. Here I have CCDD, so it doesn't look like it has that pattern. Here 0, 2, and 1, 1. So this and this is different, but these are the same. These and these are the same, and these are different. So it's not exactly the same group, but it could be the same group if maybe there's a rearrangement of A, B, C, and D that make it look exactly like this. And in fact, there is one such rearrangement. So it turns out that if I set up A to be 1, B to be 3, C to be 2, and D to be 0, then it turns out that these two are the same, and the Cayley tables would actually look exactly the same. So I would have to write my Cayley table starting with D, A, C, and B, and D, A, C, B. And then the Cayley table that is going to appear here it's going to look exactly like the Katie table that we have in here. And this is what's going to be called an isomorphism of groups. This that we have here with these choices, that's going to be an isomorphism of groups. Okay. But now, so these two are the same. And now what I would like to do is try to see how groups are different. So here's an example of classification of finite groups. So here n is going to be 8. So I'm looking for groups such that the order is 8. Okay. And I'm going to give you a few of them. For example, z modulo 8 is such a group. It is such a group because it is a group with exactly 8 elements. It consists of the classes 0, 1, 2, up to 7 modulo 8. So it has 8 classes. Now I can do another group with 8 elements by doing the direct product of z modulo 4 and a group that has 2 elements, z modulo 2. Now this is pairs of classes. This is a class modulo 4 and a class modulo 2. And now there is 4 classes modulo 4, 2 classes modulo 2. So there's 8 elements. Another type is z modulo 2 cross z modulo 2 cross z modulo 2. Now this is triples of A modulo 2, B modulo 2, and C modulo 2. This direct product is also of order 8. Now, we've also seen the dihedral groups. D4 is the dihedral group of, so this is the symmetries. Remember, this is the symmetries of a square, okay, of a regular polygon with 4 sides. So the symmetry, the rigid motions of the square, and we saw that this has the identity symmetry, and then a rotation of 90 degrees, a rotation of 180, a rotation of 270, and then the next one would be again the identity. There's also a reflection that goes through one axis, and then rs, r square s, and r cube s. These are all the elements, and there are 8 elements. And more recently, we also saw the quaternions. Hamilton's quaternions also has exactly 8 elements, plus minus I, plus minus j, plus minus k. So these are 5 groups of order 8. And now the question is, well, first, question 1, are these different? And in what sense? And question 2, are these all the groups of order 8? And the answer to this one is going to be yes. These are actually all the groups of order 8. And for Q1, the answer is also yes. These are all different. So there's exactly up to what we call isomorphism. There is exactly 5 different groups of order 8. Of course, you can do like we did over here. There can be other ways to write the groups with other labels, but they are the same group. It's just different labels for the same group. So you could write z modulo 8 with other letters, other types of labels, but it will be z modulo 8 if it's like this one. But it turns out that this is exactly it. There's 5 groups up to isomorphism. And the question is here that I want to address is, how do I prove that these are all different? So let's think about that. So I'm going to list them all here again. I have z modulo 8. I have z modulo 4 cross z modulo 2. I have z modulo 2, let's say just cubed. I have d4, and I have q8. And the way we're going to tell that these are different is by looking at group theoretic information about these groups. They all have order 8, so there is no difference there. They all have order 8, so that is not a difference, that's a commonality. Of course, if there was a group here that had order 10 or order 12, then that's clearly different because of the size. Now, what's different about some of these is that all of these are abelian, while these are non-abelian. D4 is non-abelian because, well, for example, RS is not the same as SR. Remember what the elements of D4 look like. This is a list of all the elements. SR is not here, but SR has to be one of these elements. So let's see which element is SR. So SR is the same as SR S times S, because S times S is the identity. But remember that S R S is R inverse in a dihedral group. So this is R inverse S. But also remember that R to the 4 is 1. So R cube is the inverse of R. So R inverse is R cube S. So SR is actually R cube S, and RS and R cube S are two different elements. You can see them right here, that RS and R cube S are different. Great. So we can see that then RS is not SR, so D4 is non-abelian. Q8 is also non-abelian because we know that, well, IJ is K, but Ji is minus K by the way multiplication works in the quaternions. So we see that that is not equal to each other. K is not equal to minus K, so the quaternions are non-abelian. So this gives me a way to classify that all these groups are abelian, all these groups are non-abelian, so definitely any one of these has to be different from these. So now the task is, let's try to figure out why these three are different, and then we'll figure out why these two are different. So for that, what I can do is to start to look at the number of elements of each order, for example. Or another way to classify this is that, well, Z modulo 8 is cyclic. Z modulo 8, for example, 1 under addition generates all of Z modulo 8. But Z modulo 4 cross Z modulo 2 or Z modulo 2 cubed, these are not cyclic. For example, I can show you that every element here has order at most 4. So if I have AB, a pair in there, and I multiply it by 4, what I'm going to do is, well, it's going to be A plus A plus A plus A 4 times. So it's going to be 4A and 4B. But 4A, this first coordinate is modulo 4, so this is congruent to 0. And 4B, that is congruent, that's reduced modulo 2, that is also 0 modulo 2. So this tells me that the order of every element, the order of each element, why does it do that? Is a divisor of 4. So that in particular, says that there is no element of order 8, and therefore Z modulo 4Z cross Z modulo 2 is non-cyclic. Similarly, for Z modulo 2 cubed, if I have something in here, it will be something like a triple ABC, and twice any of those triples will be 2A, 2B, 2C, which is congruent to 0, 0, 0. So every element has order 1 or 2, and that implies that is not cyclic because there is no element of order 8. So that tells me that Z modulo 8 is different from Z modulo 4 cross Z modulo 2, and different from Z modulo 2 cubed. But also, I know that there are elements in Z modulo 4 2, Z modulo 4 cross Z modulo 2. There is an element, for example, 1, 0 of order 4, but in Z modulo 2, Z cubed, no element has order 4, and therefore Z modulo 2 cubed is not the same as Z modulo 4 cross Z modulo 2, because in here there are elements of order 4, while in here every element has order 2 or 1. The identity has order 1, the rest of the elements have order 2. So from this, the fact that Z modulo 8 is cyclic, and the fact that every element here has at most order 4, at most order 2, that tells me that this is different from this and that. And these two are different because this one has an element of order 4, while this one has no elements of order 4. Great. So all those abelian groups, the three abelian groups of order 8, are different. How about D4 and Q8? So remember again that D4 is the identity r squared r cubed s rs r square s r cube s, and Q8 has plus or minus 1, plus or minus I, plus or minus j, and plus or minus k as its elements. And it turns out that, well, let's look at the, I'm going to write here the order of each element. The order of 1 is 1. Let me perhaps just write this in a different way. So I have all the elements listed here. 1 minus 1, I minus I, j minus j, k minus k. And the order of 1 is 1. Great. The order of r is 4. The order of minus 1 is 2. The order of r squared times r squared is r to the 4, which is 1. So this has order 2. And r cubed has order 4. The order of I is 4 because we have I, and then I squared is minus 1, times I is minus I, and times I is 1. So this has order 4. And you can check that minus I has order 4, j has order 4, minus j has order 4, k has order 4, and minus k has order 4. S is a reflection, and a reflection has order 2. And rs, r squared s, and r cube s are actually also reflections of the square. So this has order 2, this has order 2, and this has order 2. And now we can see that D4 has 5 elements of order 2, but Q8 has 1 element of order 2. And that tells me they cannot be the same group, because if somehow Q8 was just a different way of labeling the structure that is D4, this could not possibly happen. This count of number of elements of a given order is independent of the label that we give to its elements. So the fact that there is 1, 2, 3, 4, 5, but only one here element of order 2, tell me that these two have to be essentially different groups. Similarly, there's only 2 elements of order 4 in D4, but in Q8 there is all these many. There are six of them that are of order 4. So that tells me that both D4 and Q8 are non-abelian but different, and abelian groups are also different. So these are all different groups, and these are different groups. So all 5 are different. Now, the second question that I proposed, this one, is a lot more tricky. How do we know that we have found every single group of order 8? That will have to wait, and we will have to use better techniques to show that these are all of them. Or one could try to exhaust all the possible Cayley tables for sets with 8 elements and show that these are the only possibilities somehow. But there will be other methods to prove that these are all the possibilities for groups of order 8. Okay, so I will stop here, and then next time, what we will do is do a better job of explaining how to do this, how to prove that two groups are actually the same, and what does this mean. And that will be the concept of isomorphism, and which is the concept of maps between groups that make two groups that we can prove that two groups are the same group. So I'll do that next time.